Okay, welcome everyone to this new talk of the DIGA webinar series. So it's my pleasure to welcome today Paolo Di Lorenzo from the Sapienza University of Rome, where he's an associate professor at the Department of Information Engineering, Electronics, and Telecommunications. He also held a visiting research appointment with the Department of Electrical Engineering at the University of California in Los Angeles. His expertise is in communications, optimization, federated learning, but of course also graph signal processing or topological signal processing. He received also several awards, among which a EuroSIP Early Career Award, many conference best paper awards, also best PhD thesis awards from the Italian National Group on Telecommunications and Information Theory in Italy. He's an associate editor of several journals, and currently, or he used to be an associate editor, I think, of several journals, and currently he's a senior editor for the IEEE transactions on signal processing. So it's a pleasure to have you here, Paolo. So go ahead with your talk.
So thanks a lot, Gerd, for your kind introduction. So this talk is about task-driven topology inference for signal processing and learning of topological domain. So in a nutshell, it's about topological signal processing. So all of us are very familiar, I guess, with graph-based representations. And we all know how graphs are, very versatile representation used to model and process data coming from different domains, spanning from, for instance, biological, technological, or social networks, just to make some simple examples. But by definitions, graph representations can encode only pairwise relationships among data. And for these reasons, they are some way limited to model complex interactions that, cannot be simply reduced to dyadic relationships. There are several applications domain where this is true. For instance, in biological network, some reactions occur only when a set of genes or proteins interact with each other. In social networks, it's typical to have group kind of relationships among individuals. Also in knowledge graphs, we have, concepts that arise from merging groups of, let's say, more simpler concepts. This justify essentially goes going beyond graph representations, going toward what we call topological domains. So if you go look at, all the possible relationships that we can inject here, essentially, we can move from the left side where no relationships among data are considered to the right side where only set type relationships are present. In this case, essentially, this is, let's say, the more general case considered by hypergraphs, where essentially a set of nodes represent a group, and we might have relationships among groups under the forms of what are called hyperedges. Of course, if we add just binary relationships, we have a graph. Essentially, our domain of interest is in the middle between graphs and hypergraphs. And especially we are considering, let's say, special forms of hypergraphs called complexes, in particular, simplicial and cellular complexes, which are simple example of hypergraphs, but at the same time, they are very algebraically rich. And this, richness in terms of algebra enables sophisticated processing techniques. So what is a simplicial complex? Well, essentially a simplicial complex is a collection of simplices of different orders. So we have, for instance, zero order simplices, which are nodes, one order simplices, which are edge, and then triangles, tetrahedra, and so on. So the most important properties, if you want to have simplicial complexes when we have to build a simplicial complex, is the inclusion property, in the sense that, simplices of lower order that are phases of a simplex of a higher order should belong to the complex as well. What does it mean? An example, for instance, a tetrahedron has 4 triangle phases, and by construction, all the triangle must belong to the simplicial complex as well, by the inclusion property. Now, another topological domain of interest is the one of cell complexes. In particular, we are interested in what are called regular cell complexes, which in a way are relaxing the inclusion properties that I was talking about and it's before, and it's related to simplicial ones. In this case, let's say, simplices of order 2 in the case of a simplicial complex can only be triangle. Here in cell complexes, instead, we have the concept of cells, which admits the possibility to have polygon type relationships. So in this case, a polygon might exist that puts in relationships, let's say, more nodes. For instance, here we have a pentagon and so on, squares and so on, without the necessary, the need, if you want, to add all the triangles that are between any triplets of nodes. And this gives, let's say, more flexibility in representing higher order relationships through this different topological domain, which is called cell complexes. Now, both these architectures, these structures can be effectively represented using incident matrices. And let's say this is a hierarchical representation because we can build incidence matrices at different orders. For instance, we have incidence matrices between nodes and edge, and this is the classical one that we use typically in graph signal processing, but we also might consider incidence matrix that goes above, from edge to triangles, or edge to polygons in the case of cell complexes, and even beyond. So, for instance, these elements of the incidence matrix are 0 if, of course, the simplex of order, or the cell, in more generally of order k minus 1 does not belong, is not a phase of the cell of order k. 1 if it belongs, if it's contained, and the orientation, is the same of the one considered inside the cell, and -1 if it has an opposite orientation. So a very simple example is given by this. Of course, given this representation, it's very easy to, understand what is the relationships inside this B1. So, for instance, between this node 1 and 2, there is this edge, and this 1 and -1 are respectively, for instance, the tail and the head of this first edge that is written here. At the same time, we can build the same incidence information among triangles of a simplicial complex by including, for instance, the edge that are present inside the filled triangles. So as you can see here, there is a difference between filled triangles, which are these colored in blue, and triangles which are not filled. These are considered as holes in the simplicial complex, and essentially these are not, let's say, associated to a higher order type of relationships among, in this case, nodes 1, 3, and 7. And this is why essentially the matrix B2 has only 3 columns and not 4. Now, from the definition of the incidence matrices, we can build the higher order Laplacians. In particular, the Laplacian L1 is the sum of 2 Laplacians, okay, which is very interesting from the point of view of the processing, especially of edge flows, of edge signals. And in particular, is given by the summation of one component, which is called LD, stands for Laplacian down, or lower Laplacian, which encodes, if you want, the adjacency information between the lower adjacency information between edge, so the connectivity of edge through the presence of a common node, while LU is what is called the upper Laplacian, which encodes instead upper adjacency information, so information about if 2 edges are faces of a same, for instance, polygon or triangle. Now, once we have defined the domain, we can assign signals to these, let's say, cells at different orders. And so essentially we can assign, either real values, vectors, or more sophisticated, let's say, structures to each cell of the specific domain that we have considered. And the question then arises immediately: how can we process and learn from signal defines over these topological domains? Well, of course, there is a rich literature. Of course, here I'm not going to recall all of them, just the most important ones. Let's say the basic operation that we typically deal with in signal processing is Fourier transform and in general filtering. So this is, let's say, starts from the eigendecomposition of the L1 Laplacian, U lambda U transpose, where U is the matrix of the eigenvectors, lambda is the matrix of the eigenvalues, and the spectrum of a topological signals, again, is typically the projection of the signal onto this, bunch of eigenvectors. Now, a very nice and interesting, let's say, operation, let's say, a property that, for instance, one cell, so edge signals, have in this case is the so-called Hodge decomposition. In Hodge decomposition, the signal space of one cell signals can be decomposed into the direct summation, so of three orthogonal subspaces. The first one is called the gradient space, the image of B1 transpose. Is also called often the irrotational component of a signal, of a flow signal. The second one is the curl space, is the image of B2. It's also typically called the solenoidal component. And the last one, the kernel of L1, is the harmonic space, which contains signals that has no irrotational and no solenoidal behavior. Okay. So since this is an union of subspaces, of course, also the eigenvectors can be, let's say, decomposed in, let's say, different parts associated to these different subspaces, and this gives a lot of interpretability of the topological Fourier transform operation. Now, based on that, people have also introduced the concept of, topology. People, a lot of people that are connected here, the Earth first, then Elvin that I've seen connected, have proposed this concept of topological finite impulse response filter, which hinging essentially on the Hodge decomposition is built on the summation of three components. A first one, which is given by polynomial of the upper Laplacian, which aims to filter, if you want, the curl component of the signal. Another one, which is h of LD, which is polynomial in the down Laplacian, in the lower Laplacian, which instead meant to process the gradient component of the signal. And plus the last term, which instead, can, let's say, weight the harmonic component. Now, of course, there is a lot of literature. It's actually a rich field, both topological signal processing and topological deep learning. So I apologize immediately if you don't see maybe your contributions here. I couldn't add more, lines in the slides. But I mean, now the focus of this talk, after this very short background, is on task-oriented topology inference methods. Okay, so what's the point? So most topological signal processing tools assume perfect knowledge of the underlying domain. So the question is, if we have missing or partial knowledge about the relational structure, can we infer the topology from the data? Now we will consider two scenarios. The first one is that the lower connectivity is known. What does it mean? It means that, let's say, the one skeleton of the complex, so the underlying graph, is known, and we want only to learn upper relationships, so the presence of polygons or triangles, from, for instance, edge or node signals. The second case, which is also most challenging, is when no relational information is available. And in this case, the topology must be learned from scratch, given nodal observations. But let's start, let's say, step by step with a classical signal processing approach, which comes, as typically it is, by defining a total variation. So this is what is called the curl total variation for an edge signal x1. Essentially, is the sum of the squared curves, the squared curve behaviors overall, for instance, the triangles. So aijk in this case is an indicator variables which identifies the presence, if it's one, of a triangle between edge I, J, and K, and these other are the components of the edge signals which concur in the computation of the curve. And of course, you are summing over all the possible, let's say, edge combinations and then possible triangles. Of course, this can be written in a, let's say, matrix form by, using B2, the matrix B2, that relates the incidence between edge and triangles. And starting from that, we can, let's say, try to learn the upper topology by parameterizing B2 in this manner, where essentially these variables Tn, which are indicator variables 0 and 1, appear, and they identify the presence of a triangle or polygon in the complex, where Bn and Bn transpose, of course, are the vectors that identify the incidence relationships. If we plug B2 inside the previous total variation, and we assume that we want to learn the topology from a given set of collected edge signals, let's call it x1, the inference problem can be formulated in a very general, fashion, which is like the minimization of the total variation of the curve total variation that we have seen before with respect to this indicator variable t assuming the fact that we give a certain number, T star, of triangles that we expect to observe in the topology. This problem can be solved, let's say, in closed form very, very easily. So just, these trace values can be listed and ordered in ascending order, and you can just, take the indices of the first T star elements that leads in the end to the triangles that will have the minimum, the signals with the minimal curve behavior. So in the end, this minimization of the total variation proposed in this paper by Sergio Barbarossa and Stefano Sardellitti aims to identify triangles that have a minimum curve along the edge. But of course, depending on the task, we might have the learning task at hand with which we want to, process our signals. We might, have one topology or another topology. And the goal would be, in the end, learn the best topology for the given task. And this typically requires a joint optimization approach. So let's try to abstract a general problem formulation. So let's suppose that we have an objective function f for the learning task to be optimized. And this task, let's say, has some task-specific parameters, w, that belongs to some set calligraphic w. So it's clear that typically the problem can be formulated as the joint optimization of the topological representation encoded in T and the task-specific parameters encoded in W that minimize jointly the objective function f. In the following, I will give you 4 examples of this, let's say, very general problem formulation applied to specific signal processing and machine learning tasks. The first one is topological dictionary learning. So what is dictionary learning? No? It's a technique where we want to learn the parameters of a dictionary such that it's possible to represent data in the more sparsest, parsimonious way as possible. So our approach essentially extends a work done by Dorina, who is connected in graph signal processing, generalizing it to the case of topological signals. So we build an over-complete topological dictionary made of several, let's say, filters, H1, H2, HP. Each one essentially is built on the FIR filters proposed by Elvin and Gert that I showed before. And the coefficients of this filter, H, U, HD, and so on, are collected into a vector, H, which represents essentially the vector of all coefficients that we want to learn. But of course, if we here are assuming that only the lower Laplacian is known, so in a way the lower connectivity is the only available information in terms of relational structure, LU becomes essentially an unknown. And so we can actually parameterize a LU in a very using the same parameterization that we have seen before for B2 and making it appear the variable T, which is an indicator variable in terms of which polygons or which triangles, depending on the complex we are considering, are present in the topology in order to build a dictionary that will depend not only on the filter coefficients, but also on which upper topological structure we are dealing with. Then, of course, these dictionaries have a very nice localization guarantees in the sense that, they have a very specific frequency kernel behavior and localized component both on the J-hope lower neighborhood and upper neighborhoods of the cells. And in particular, if these kernels are chosen to satisfy specific assumptions that, could be guaranteed by the careful choice of these coefficients, of these filter coefficients, Hj. Actually, these dictionaries build some topological frames that can be very useful to represent signals, topological signals in a sparse fashion. But without going too much into the mathematical detail, let's go to the myth of the joint topology inference and topological dictionary learning. Let's suppose to have a training set of, let's say, M flow signals that we collect into a matrix Y. Okay, so the problem is cast as the joint minimization of what? Of the filter coefficients H of the dictionary, of the topological, let's say, structure T, of the sparse representation S of the signal Y, subject to, in order to minimize essentially the squared error of the representation, plus a regularizer, of course, that is useful to regularize the problem, and some sparsity constraints on the sparse representation, some constraints that guarantees essentially the well-behavior, the good behavior, if you want, of the found dictionary in terms of frame theory, and the fact that T should be, an indicator variable. It's either 0 or 1 to identify the presence or not of a polygon inside the complex of interest. Now, this problem is pretty complicated for several reasons. It's non-convex because of these sparsity constraints of this, let's say, discrete set. And so what we propose is our approximate iterative solution. The first one is the following. So let's suppose that for a moment that the topology is fixed. If it's fixed, one can alternate between the dictionary update and the sparse coding in a, let's say, pretty efficient fashion. Why? Because the dictionary update can be rewritten as a quadratic problem, and so can be solved pretty easily. The sparse coding can be, solved, even if not in closed form, but, can be approximated efficiently by, for instance, orthogonal matching pursuit. So alternating between these two methods can, given a topology, provides a good, let's say, proximal of the best dictionary parameters and the sparse representation for the given topology. So our approach is a greedy one, in the sense that we start from a full topology, so T is equal to all 1. We run this algorithm, and then we remove, at the end, after convergence, the polygon that leads to the largest reduction of the objective function. And this actually helps, in a way, to refine the topology iteratively and in a greedy fashion until we find that there is no more incentive in removing polygons, or we ended up with the, removing all of them. In this case, it means that no higher relationships are useful to represent the task in the data in a sparse fashion. Of course, this works very well. I mean, it works pretty well, but it's very complex, of course, because, we have to do this greedy search, and then every time we have to run these alternative optimization algorithms, and then to relax, to, let's say, simplify, we propose also a relaxed algorithm, which in a way works like that. I would jump just here a moment. It's just if we relax these constraints, so the Tn belongs to 0, 1, to the interval, and it's like if we are adding here a sparsity-inducing penalty in order to promote sparsity of the representation, of the topological representation. So this means that now we can actually alternate between 3 steps, one that is the dictionary update, one that is the sparse coding, the other one is the topology update, which is just done in terms of a proximal gradient descent algorithm that performs, gradient descent, but then there is a proper thresholding function, which, we are pretty free to choose, there are several of them, that can be used to promote sparsity of the topological representation. And this is, a relaxed version, but it's much more, let's say, much less complex. Now, these are some results. So for instance, this is the normalized mean square error versus the number of non-zero coefficients for different parameterization of the dictionary. So this is the results achieved by topological Fourier transform. These other ones are different topological dictionaries that we parameterize in a different manner, for instance, only using edge Laplacian information, joint Hodge Laplacian, or our separated Hodge Laplacian, which is the red one. While the last curve is the one where we not only optimize the dictionary, but also we jointly learn and infer the best topology for the specific task. And it is clear that if we learn jointly the topology together with the parameters of the dictionary and the sparse representation, we get a nice gain in terms of error representation. Here instead we show on the right the error rate of the topology inference algorithm with respect to the number, to the percentage of true triangles that are present in the complex. Actually, this shows that if the percentage of triangles is sufficiently large, so in this case larger than the 60%, both methods, so both the relaxed and the greedy, which are respectively the blue and the red, actually learns perfectly the topology. it starts to be much more complicated, the learning of the topology, when the percent of triangles is much lower. Why? Because in this case, essentially, it starts to be true, and this is even more true for larger value of sparsity, so increasing the number of non-zero coefficients of the representation. It starts to be true that, you know, more topology becomes, let's say, sufficiently good in representing the signal with the same mean square error. And this gives rise to a kind of ambiguity in the sense that probably the mean square error in this regime could not be a good proxy to estimate the topology. So we have also an example on real data that shows that our method, you know, is very effective in representing this, let's say, traffic data of this German National Research and Education Network. It's actually a telecommunication network with traffic flows with respect to, again, topological Fourier transform and these other methods which are analytical dictionaries based on Hodgelets, so the generalization of wavelets to topological signals, and topological Slepians that we have proposed some years ago. And as you can see, these topological dictionary learning methods can indeed get a lot of gain, probably one order of magnitude in this case, thanks to this joint learning of the dictionary and the topology. And interesting also, this method is able to infer, let's say, a consistent topology across different values of sparsity. So here, for instance, is 13, 17, 21, the level of sparsity that we are considering. And the colored polygons are the ones that we indeed infer. But the red ones are the, let's say, persistent ones. And so we can see that some of them persist, if you want, across different values of sparsity, let's say, justifying the fact that these are the real polygons that are useful to explain the, if you want, the solenoidal behavior, the curve behavior present in the traffic data in order to be able to compress them. Okay, the second task, let's move to another task now, is topological adaptive filtering. Now, in this task, typically in topological adaptive filtering, what we have an unknown filter, an unknown system. We just inject an input, we observe the output, and we want to infer the structure of the impulse response and possibly to track it over time, right? So let's translate this into the topological signal processing domain. So let's suppose that we observe xn, which are stationary edge flow signals that are processed over time through linear shift invariant graph filters. So let's suppose that what we observe is essentially the result of a linear time shift invariant graph filter operations that work essentially on the upper domain and on the lower domain respectively with different coefficients, which we call HMU0 and HMD0. Of course, we observe this plus noise, but we assume also to observe them over just a subset of nodes, defining a sampling operator dn, which is just a diagonal metric that collects data over just a few set of edges. So the question is, okay, knowing partially, if you want, the topology, just in terms of LD, so LU is not known, and knowing the flow signals X and Y, is it possible to estimate and track at the same time the H, so the parameters that give rise to the signals that we are observing, and at the same time the structure of the topology of the upper topological information? So the problem is formulated essentially as a, least mean square problem, which will give rise to what I call topological least mean square algorithm. So we want to minimize the expectations of the square of difference between the observed data at time n and its, let's say, representation as it was written before. This is just its compact matrix version, which makes explicit the vector of coefficient h that we want to learn, and the topological information T, which is embedded into this regression matrix X, which has, as this structure, which has, all the power of the Laplacian, upper Laplacians and lower Laplacians. And the explicit dependence between the topology is encoded here inside LU. So we will have LUT, LU to the power of 2t, and so on. So the algorithm that we've developed is the following. It's called topological least mean squares that essentially performs a joint optimization of these objective functions, where this GT is actually a sparsity-inducing penalty, again, on the variable t. And it performs, let's say, a stochastic gradient descent on both directions, both on the coefficients update, leading to this recursion for the age, and also to the topology update, leading to this other recursion for the topological update. Again, gradient descent plus a proximal operator that enforces sparsity. Now, the good thing of this, let's say, method is that under certain condition, we can, without going too much into the mathematical detail, but the clue here is that under certain condition, the sampling operator and on the step size of the recursion, we can guarantee convergence of this method with a given, let's say, convergence rate up to a mean square deviation at convergence, which is given by this given expression. Now, the good point is that actually this requires the assumption that if you want the topological least mean square algorithm is able to learn over time the true topology. And actually this is verified in a actually very broad range of experiments that we have by numerical results. So this is the mean square deviation over the coefficients over iteration index. So these are classical learning curves of adaptive filters that converge, let's say, to some steady state floor, which is the MSD that we have predicted before. So these, let's say, dashed curve here are the prediction, right? So theory match the results. But the interesting one is this other one, is the MSD on topology inference, which tells you the learning curve in terms of error in terms of topology approximation. So as you can see, no matter if there are 10% of triangles, 30% or 40%, this topological least mean squares is very good actually at learning the right topology. In a few number of iterations can drive the topology error, inference error to 0, and then let the right learning of the filter coefficients that gave rise to the signal that we are observing. And this justify the approach and the fact that you want to learn at the same time the best, let's say, topological representation in terms of adaptive filtering and the topology that gave rise to the data that we are observing. Now, task 3, last two tasks. Up to now, we have, let's say, considered, let's say, more or less classical signal processing task. Let's move to topological deep learning. We want to apply now this story to topological neural networks to perform, let's say, more general tasks, for instance, graph classification or, node imputation to data that in principle, in this case, have no relational structure. So let's assume now that differently from before where we were starting from the knowledge of the lower adjacency informations of the graph. Here, the data are just associated to points. No relational information is present. So what we have proposed here is what is called the differentiable cell complex module. Is essentially a neural network model, is a layer of a neural network model that performs two steps, essentially given a bunch of nodes, associates a topological space, in particular a cell complex, to the data. And once essentially the data are associated to a cell complex, it passes this same cell complex data to a topological neural network, which is composed by the stack of a graph neural network that works on node data and a cell complex neural network that instead works on edge data. But of course, for doing that, we need, to define this operation. So how can we do indeed this differentiable cell complex module? Now, despite this, let's say, diagrams could be a bit ugly at first sight, the concept is pretty simple. So let's suppose that we have some edge features on input and possibly a graph. I mean, this is not necessarily needed, but if we have it, let's say maybe a non-perfect graph, we can give it an input in order to get a refinement. Then what we do is we compute an embedding of these node features. Let's call this X0 auxiliary. Then from these auxiliary node features, we compute some similarities among all the pairs of possible node embeddings, okay? In order to understand which nodes have, let's say, more similar embeddings in terms of node features. Then we essentially associate to each edge, to each possible edge among these node features, the ones that minimize this alpha and max function, which solves essentially a problem, which tries to learn, in a nutshell, a sparse probability vector that associates essentially larger probability to more similar, let's say, to edge that connect more similar nodes. And so in the end of this operation, we get a sparse probability vector, and the nodes that gets a probability, the edge, sorry, that gets a probability greater than 0 are just added to the topology. Then after that, we create essentially this graph through what this module that I just described, which is differentiable graph module. We essentially have to understand which polygons are there in order to build a cell complex. But to understand which polygons are there, we need the edge signals, while at the beginning, we started only with node signals. And so we need what we call, in the machine learning literature, what is called an uplift module. The uplift takes the node signals and produces in output corresponding edge signals, okay, through a learnable transformation. Now, knowing this edge signal associated to the edge of the graph that was learned previously by the differentiable graph module, the polygon inference module learns instead polygons by applying a technique that is similar to the one before, always the alpha and max. But in this case, we are computing similarities inside the polygons. So we associate, let's say, a measure of similarity to each polygon. We run the alpha and max, and essentially we associate a probability of existence of each polygon that if it is greater than 0, then the polygon is added to the complex. Now, once the polygon is essentially built, we do two message passing, one at the node level and one at the edge level message passing. These are, let's say, classical, let's call it cell complex convolutional neural networks. And then we ended up into a node feature x0 int and an edge feature, which is then downlifted in order to provide a corresponding node feature, which is then concatenated with the other that comes out from the node level message passing to come out with a final node feature, which is given in output by the overall differentiable cell complex module together with the cell complex representation that is passed to the next layer of the network. So just to give you an idea, an insight of the possible let's say, benefits that we might have from using this representation. The larger benefits are, in the case of, we don't know a graph on inputs. So let's suppose that we are considering a graph node classification problem or several, let's say, benchmarks, Cora, CiteSeer, PubMed, and so on. These are homophilic, let's say, data sets. In the case where we don't know the graph on inputs and we actually compare our results with other techniques that in principle are able, either to, learn the graph from scratch or, work with the data that they have, we understand that often our approach, gets state-of-the-art performance with a lot of, performance improvements in several cases with respect to the state-of-the-art. And this is true also, this is less true if you want if a graph is available on input, just because it's not always true that in this kind of data sets, injecting higher order information could be beneficial at all. Sometimes it might not be true, and this is reflected by the fact that maybe our architecture might not beat, for instance, graph attention network of graph convolutional networks. So this is also true in the heterophilic case, where actually we get pretty good results, especially without the graph given on inputs, thanks to this rewiring capability of our scheme and the possibility to inject higher order information that was not present in the previous architecture. So just to give you also a pictorial example of what the system learns, let's suppose that we are here on an heterophilic dataset, which starts from an initial graph that is completely, let's say, wrong in a sense that connects points of the data that belongs to different classes. After a while, after the learning, our method is able essentially to prune or to rewire the graph, if you want, and the complex, in order to connect to privilege connection only between elements belonging to the classes. And this is, something that is learned by the method itself in a task-oriented fashion. Last task, and I should finish in 10 minutes. Do you have time yet for
yes, 10 minutes is fine, yeah.
Yeah, perfect. So the last part is related to what is called cellular shifts on graphs, okay? Now, up to now, we have talked about simplicial complexes and cellular complexes as a way to go beyond graphs. Cellular shifts is another powerful mathematical framework that is able to enhance graph-based learning models, by adding both relational and topological information. So in a nutshell, given a graph G, a cellular sheaf essentially associates to each node of the graph a vector space that we call the stalk over a node. Then we have a vector space over an edge, and this is called the stalk over an edge. And then we have a linear map that we call FVE, which is essentially a mapping between from the vector space defined over the node to the vector space defined over the edge. Now, this, let's say, richer structural information gives much more degrees of freedom in modeling and processing the signals that we might deal with in practical applications. Now, once we define essentially these vector spaces over the nodes and over the edge, we can define what is called the co-boundary map. It's a generalization of what we see in graphs. Typically in graphs, we have just, let's say, given the data associated to different nodes, we will have a simple, let's say, difference relationships within this data. Here instead, existing these, let's say, maps, these restriction maps, between nodes and edge, essentially this difference, these co-boundary relations, is weighted by the presence of these linear operators, FVE minus XV minus FUE XU. And then defining essentially the co-boundary map over the sheaf, it's possible to define the sheaf Laplacian, essentially, by just defining delta transpose delta, where delta is this co-boundary map. Essentially, the sheaf Laplacian is it can be seen as a block Laplacian matrix, where each block is, let's say, given by this expression and depends on these linear mappings, these restriction maps that exist over the topology of this graph. Now, the problem that I want to, let's say, formulate here is essentially sheaf Laplacian learning. So we want to learn, we want to understand, given data, what is the structure of the sheaf Laplacian, imposing a smoothness assumption on the signal X. Now, here the interesting thing is that the structure of the sheaf Laplacian is determined by the existence of an edge, and the existence of an edge also brings with it the existence of a proper restriction map, which must be learned jointly with the topology. And this is where, the interesting thing comes into play, because it becomes a joint optimization of the topology structure, and at the same time, the restriction maps that give rise to that topology. But in order to make this evident, to make this appear, we have to, let's say, manipulate a bit the total variation. So what we want to do in the end is minimizing, with respect to the sheaf Laplacian, the total variation of the signal can be written, let's say, in the classical way, X transpose LF X, the trace of this matrix. Now, expanding the total variation, actually, after very, easy steps, we can actually transform this global structure, which depends on the entire sheaf Laplacian, in the sum of local consistency relations that happens over the edge, and that depends indeed on the presence of these maps, these restriction maps. So given these, let's say, relationships, which is the key insight that we are bringing here on the table, essentially we can formulate the joint learning of the graph and the restriction maps in terms of minimization of the total variation over the sheaf, subject to the fact that we want to learn only a subset of edge, with cardinality E0. And at the same time, the maps that we want to learn, you know, should belong to a set that avoid the trivial solution, okay? Now, the good thing is that this problem, again, can be decomposed over the edge. So there is no coupling among the edge. So for each of them, we can, in principle, compute the best restriction map that minimize this variation associated essentially to the subject to the constraints that we are imposing. And then again, as we did that before at the beginning, we list all these contributions in ascending order, and we just collect the first E0 elements that represent the edge with the associated restriction maps that leads to the minimum total variation of the observed signal. Now, the only point remaining is the following one. So how is the local problem built? How is the expression of the local problem? Well, it depends on how we select this F. So how we selected this, let's say, constraint. Now, of course, there are several possibilities. Here we consider, let's say, starting point, a simple case, where actually the data x, u, x, v, that was defined in the previous slide, so the one associated to each node, is represented over a common dictionary, xu equal to du su, with a certain given sparse representation, okay, which essentially reflect the fact that nodes at different, the data at different nodes might reside, in principle, over subspaces of different dimension. And this different dimension is reflected into the sparsity of SU. And then the maps, and this is, you know, also a simplification in general, are assumed to be square and orthogonal, okay, orthonormal. In other words, what we are looking for in this formulation are rotation matrices, okay? And it's easy to see that this problem here can be recast in an equivalent manner by setting this restriction map FVE equal to the identity and looking only for one of them, so one restriction map, restriction maps, FU, and in particular, the one that maximizes these trace, subject to these constraints. Now, this is a very simple, if you want, procrustress problem that admits a closed form solution. And in particular, taking the singular value decomposition of this matrix, the optimal map is just given by the product of the left and right singular vectors achieved by this matrix here. Interestingly, the value of this trace, that in the end it will also act here by, in the selection of which edge will be present or not, depends, if you can see, by this, let's say, product SUSV. If you want, this can be seen as a cross correlation, if you want, between the representation of the signals over the two different spaces, right? So it's clear that if there is a high correlation among the representations of the signals over these two spaces, now it will be more easy for the transformation, for the restriction map, to align this data, and then it will be more probable that the edge will be present. If instead this correlation will be, cross-correlation will be close to zero, probably, the map will not be enough. It will do its best, but probably the variation in terms of difference of the squared written here will be a large value, and then probably that edge will not be selected into the graph. So just to give you an example of possible results, here we are considering, the total variation achieved by our method with respect to the possible number of edge. considering the proposed sheaf construction, which is the one in a continuous case, and instead a naive graph construction, which does not take into consideration the presence of the maps, of the fact that you can, let's say, align the data through these restriction maps, but only, let's say, based on the distance between the subspaces spanned by the dictionary, the elements of the dictionary. And what happened is the following, is that thanks to this alignment property, to the fact that we are not learning only the, a relationship, the existence of an edge, but also the map that tries to align the data present of the nodes, actually we can achieve an overall total variation over the found sheaf that is much lower with respect to a naive graph construction based on, let's call it classical graph signal processing approaches. An example here that is, let's say, more, let's say, a visual example is this one. For instance, the colors here of nodes are associated to nodes that live in subspaces with equal dimension. So the green one, the yellow one have the same dimension in terms of subspaces, and the red one, again, have the same dimension. If we now just look at the similarities without considering the maps, but let's say the classical mean square error between the data associated with this node and this other node, you might end up into, adding an edge, because you might find that these two nodes indeed are similar, but similar with a very high total variation that is seen like that. Instead, if we actually are able not only to learn the topology, but to associate to each edge a map that is able to align this signal, we ended up to this result. And this result is actually much better than this other one, because it's able to, if you want, perform a semantic network construction. What does it mean, semantic? It means in this case that nodes having, let's say, similar semantic information in terms of, let's say, data generated by similar subspaces are connected together, while, let's say, other nodes that, have different subspaces, different, if you want, semantic informations, are, let's say, not connected with them. I think that's, I made it in time. Good. So just to conclude, in this talk, essentially, I gave an overview of the recent results that I achieved with, my students and my collaborator on task-oriented topology inference, considering different learning tasks, spanning from dictionary learning, adaptive filtering, topological neural networks, and now finally cellular sheaves. Of course, there are several interesting research directions. For instance, directional topologies. There is a very nice paper now written by Elvin, Isufi, and Claudio, one of my former students on that. Definitely worth to read. Also, scaling topology inference to large systems is really challenging because, the inherent combinatorial complexity that we have in, enumerating cycles and so on. The joint spectral processing of multiple topological signals is also something that needs to be investigated. There are some tools, like, for instance, the Dirac operator, but, further investigations in this sense are useful, and especially, if you can then process all these, for instance, node, edge, and cell signals together, this might, also improve, for instance, topology inference methods thanks to this, interplay between the signals at different orders, and several other directions. I invite those of you who are interested to read this recent tutorial paper that we have written for signal processing. And I guess that's it. I thank all of you for your attention. If there are any questions, I will be very happy to discuss with you.
Thanks a lot, Paolo. Very, very nice. Yeah, very exciting directions. Any questions for Paolo? So you can, either unmute yourself or put them in the chat, whatever you prefer.
Hello, thank you very much for the nice talk. I have a question regarding the neural network that you have shown. The kernels that you have applied. So you said that they are like conventional neural networks, so conventional convolutional, I mean. Did you apply it? So how it could be conventional because you have a certain topology here.
Yes, I would say conventional topological neural network. I mean, the classical topological convolutional neural networks are there since, I guess, 2 or 3 years right now. I call conventional something that is then, it's not like the classical convolutional, the one that works on image. It's the classical in the topological sense. But the point here is that given that kind of architectures that are there since 3 years, the point is that those architectures require a good graph or a good topology to work in an efficient manner. And this differentiable cell complex model in a way is a module is a way to augment this architecture in order to provide to them a good topology in order to perform the learning task in a task-oriented fashion. So this is what I meant. Sorry for the misunderstanding.
Okay, thank you.
Yeah, there's also a question in the chat whether the complexity of LMS and the topological LMS, whether there's any comparison possible, or
I will check. Complexity of LMS and top LMS. Can we compare? Where being an LMS algorithm, type of algorithm, it's always going to be linear in the dimension of the parameters. Of course, in this case, you can see, you can see this, the recursion will be here, the complexity will be mainly given by the product of this matrix by this vector. So I would say that given the dimension of the topology, in this case of the graph, so the number of edges in these cases will be, let's call this M. It will be O of M, the complexity.
okay. So related to this, to this slide. So I had a question, related to this, the function of T, so of these triangles. So this is highly non-convex and non-linear, right? So I guess because you get powers of the Laplacians, so the T is, so I guess the derivative is kind of ugly, right? So, or you can get easily stuck in a local minimum, no?
Yeah, this is what I thought at the beginning, indeed. I was saying a lot. Look, there are these powers. I would say let's start with just the Laplacian at order 1 without a power of order 2 or 3 or more, just because in this case it's easier, right? He was doing it and he was always getting the right topology, and it was like, wow, this is strange. Even if the overall derivative with powers was very ugly, even it's possible to write it in closed form. But then he was trying it, with higher order powers, and actually the result is that he can always get the right topology. This is, if I well remember, this simulation with powers of order up to 3 or 4, which means that in the end there is something intrinsic that even if it's non-convex, in the end probably there is like a very large basin of attraction or toward the global minimum, such that in the end this joint optimization, even the joint makes it non-convex, in the end performs very well.
Okay, yeah. Good to know, yeah, nice.
Yeah, well, I was surprised too at the beginning, but that's your same question.
Yeah. Any other questions? Maybe I have one more, related to this adaptive filter. So you consider whenever you do a hop in the graph, you also have a hop in time, right? On the previous slide, so or the previous, this one. So
Yes,
the model of your filter is like you have, let's say, it's kind of autoregressive both in time and in the graph, right?
Yes.
But this could be, I guess, more general even, right? So you could have, let's say, different hops in time and the graph, right? Yeah.
Absolutely. You can make it more general and you have, let's say, kind of a, complexity performance trade-off if you want to.
So, and this could work also like autoregressive, I guess, right? To do prediction
which
or something.
Which is what, Helbin has done in one of his recent papers on simplicial vector autoregressive. Yes, it becomes very similar to that work in that case.
Okay. There was like a follow-up question on this LMS in the chat. How does the signal needs to be modeled for the topo LMS?
Well, yes, of course it depends. I mean, if you have synthetic data, of course, we have modeled it, to adhere to this model, okay? And this is, of course, let's say, a clear assumption that we make in order to be able to learn the true topology. But we have simulations that show that these methods actually leads to meaningful topology also over real data. And actually leads to much more meaningful results with respect to topology that are chosen in another naive fashion.
There's another question in the chat, again by Faize. Maybe you can unmute again, Faize, if you want.
Yes, in my impression, the purpose of this conjunction between dictionary learning and topology learning is to do some kind of dimensionality reduction. If we learn the topology, is there any guarantee that we also learn the optimum dimension, the optimum lower dimension? I mean,
I don't think that I can claim any kind of optimality here of any sense, in any sense. What I can show that this algorithm in a way is effective and robust in finding very sparse representation, which means lower dimensions over which your data can be represented. And that's the topology learning coupled with this sparse representation mechanism can help in further improving the performance. But definitely, I guess that it's very hard to find, let's say, theoretical condition that tells you that this is the best one. I can say that it works pretty well, but the best one, don't know.
okay, thank you.
Paolo, maybe a quick question on the dictionary learning part, just to follow up on that. In the real world examples that you showed, how do you, and in general, broadly speaking, how do you decide to go with the topological dictionary learning approach or a classical dictionary learning approach that just takes into account the graphs, right? So what is the characteristic in your data? How do you evaluate it? Do you have any heuristic or any guide on how to go with one approach or the other?
Well, very good question. In general, the hope that this kind of topological approach can work is that in a way a given topology is present, like in this case the data comes from a network, and the network are injecting some kind of spatial correlations that can be, let's say, captured by the topology. And this topology can leads to several kind of flows, which might be the components I was talking about before, and rotational, solenoidal, that can be in a way captured by the dictionary in a localized fashion and then leads to sparse representation. So in all, let's say, the cases where you have data that comes from network-like structures, telecommunication networks, water networks, power grids, and so on, I expect that this kind of, let's say, flow behavior that are hidden in the signal could be well captured by this dictionary learning construction. If you instead talk about very general data that in principle don't have a topological or a network-like structure,
I think, no, my question is more, if assuming that that there is a network structure, how do you decide if you want to take into account higher order interactions? Or
okay, the first trivial thing that I would do as a very trivial signal processing guy, I would take the signal and we would project them onto the space, on the curl subspace, which is the subspace that is, let's say, dependent on the presence of higher order information. Now, if this, the quantity, the energy of this component is sufficiently large, it means that, it's meaningful. This component is meaningful in the signal, and, processing this signal using higher order information can get better performance with respect to classical graphs. If it's not, almost zero, it means that there is no gain of using higher order information. Just use the graph. This is, let's say, zero level response of
no, I think it makes sense. Yeah. Thanks.
But of course, there are more sophisticated things that you can do if you put neural networks on top, but this is, let's say, the simplest one.
Any other question? If not, then I think we can wrap up here. So thanks again, Paolo, for this nice presentation.
Thank you.
And then I think the next talk will be end of April somewhere. So it's yeah, a little bit less than 2 months. So then I hope to see you